Leah here from leahforsci.com, and in this video we're going to look at the reaction energy diagram for the Sn2 reaction. First, a quick review of the Sn2 reaction as I teach in the substitution elimination video series linked below. Sn2 stands for nucleophilic substitution, and 2 tells us that it's a bimolecular reaction. Bimolecular does not mean 2 steps. Bi means 2 molecules reacting at the same time. In this example, we'll take a look at the energy diagram for CH3I reacting with NaSH to give us CH3SH plus NaI. The rate of an Sn2 reaction is equal to some constant K times the concentration of the substrate, that would be the CH3I, times the concentration of the nucleophile, which would be the SH-. The substrate and nucleophile react together in a single-step bimolecular reaction. This is important to help you recognize the energy diagram for an Sn2 reaction. To understand the reaction, let's first look at the mechanism, where CH3 is attacked by the SH-. The nucleophile SH- is going to attack the carbon holding the iodine, which will then kick out the iodine in a backside attack. Notice there's no sodium in the mechanism because it's simply a positive spectator ion that does nothing to the reaction. Our product is going to have the SH now bound to the carbon with an I- floating around somewhere in solution. Let's move the reaction down so that we can understand what it looks like on an energy diagram. An energy diagram simply tells us the energy of a reaction as the reaction is happening. I like to think of it as we start the reaction, and as time passes, what happens to the energy of the molecules? The y-axis measures energy. The x-axis, which is called the reaction coordinate, can be thought of as time. At the start of this reaction, we have a CH3I at some low enough stable energy. Notice we're not using numbers. I'm focusing on the concept of the increase and the decrease. In this Sn2 reaction, the S is going to attack the carbon, which kicks out the iodine, but it's not just going to happen on its own. We need to put energy into the system to allow the molecules to adopt this relatively unstable state, because even though the reaction is ideal in the long run, the intermediate, the process of breaking and making bonds, requires a lot of energy. And so we need to put enough energy into the system to almost motivate the reaction to happen. That big hump of energy that the molecules have to overcome is called the activation energy, or EA, which I think of as energy of activation. The very top of this hump, that highest point of energy, is called the transition state, which you represent with this symbol. The transition state is not an intermediate. Instead, it's almost like an in-between. In that transition state, we have a very unstable system that looks something like this. The carbon in the CH3I is bound to 3 hydrogen atoms and was bound to an iodine. But when the sulfur comes into attack to form a bond to carbon, the bond between carbon and iodine is going to break. The stronger the bond to sulfur and carbon, the weaker the bond between carbon and iodine, until there's a complete carbon to sulfur bond and iodine is gone. That would be the result of this reaction, but the in-between, where the bonds are half formed and half broken, that is the very unstable, not isolatable transition state, which has a partial negative charge as the negative sulfur is losing the charge by forming a bond, and a partial negative charge on iodine as the neutrally bound iodine is now kicked out to gain an extra pair of electrons and a negative charge. Once the bond is fully formed and iodine is fully kicked out, the molecules are happy and they release all the extra energy to form a very stable final product, which is now the CH3 bound to the SH with an iodine somewhere off in solution. A couple of key things to recognize on this graph. Since we're measuring the energy, the starting molecule in this case is relatively decent in energy. But if we compare it to the energy of the final product, you'll notice that the final product is lower in energy because it's more stable, and that gives us a negative delta G for a spontaneous reaction. But even with this being a spontaneous reaction, you still need that high activation energy, because without that energy, without the motivation to kickstart the reaction, nothing's going to happen. The key thing to recognize in an Sn2 energy diagram is the fact that we have one reactant, one product, and only one transition state. What we don't have are any intermediates. As a reminder, an Sn2 reaction is a bimolecular reaction, two molecules reacting at the same time. That means there's no intermediate, and as soon as they're done reacting, we get our final product. For a more in-depth review of substitution reactions, first, give this video a thumbs up, and subscribe to my channel to make sure you don't miss out on any more videos. Then, go watch the substitution elimination series from the beginning, which you can find on my website along with a practice quiz and cheat sheet. See the link below or go to layerforsci.com/substitution elimination.